Boom. Okay, cool. Just going to check if I'm actually live, and then we're good. Uh, uh, just realizing I live in a cool. So I live in a pretty young area of town. I stay in Cape and in Cape Town, and I'm realizing that you can hear all the cars and all the loud cars and all the loud motorbikes from my office into my headphones. I mean, I'll try and make sure that doesn't interrupt the sessions, but yeah, I mean, we'll see about that. But let's get started. So, someone's knocking. Just a moment. Do you want to come in or what? I'm busy right now. Okay, cool. So, yeah, um, where did we finish off last time? I think last time we finished off with kind of like a functional description of I squared C and how I squared C works on the STM32 board um, or chip. I think what we're going to do now is kind of because this is the second stream, yeah. So we're going to do the initial work, which is going to be like, I think we're gonna do all our bit definitions, discuss them as we kind of like cover them, and then after that, we can do some initialization work. Maybe we won't finish initialization. I swear it's quite a complicated, or rather involving protocol. So I'll see if we can finish initialization today. But gladly, I think after initialization on Friday, we should be able to finish TX and RX APIs. Let me release this one. Okay, go. Thank you. Bye. Go. I'm busy right now. Yeah, I'll come play later. Okay, cool. Thank you. That was a visit from Luke, my kitten. Yeah, so I think that's good. Let's start from there, and then we'll kind of keep going and see where we end up. But the aim of today is to finish up having done peripheral initialization. If we can get to peripheral initialization, cool, then we'll look really good. Okay, so I think the first thing we would want to do is add we would need to basically add peripheral addresses, and this is just to so we can have a thing called I squared C, and we can use it. So let's add that, and then we can go. So I'm in the memory map of my I'm in my memory map here, and what I'm going to do is basically going to find all the I squared C peripherals and add them into my MCU specific header file. So let's find I squared C, I squared C2, I squared C1. I think the Bluepill board only has two I squared C peripherals. And I'll see that they're off of APB1 bus, and APB1 bus, I still think too, it's 5400, 5800. So let's go back to our code. Let's start adding that. Cool. So peripherals, APB2, APB1. Oh, I already have I squared C1, I squared C2. 5400, 5800. I think that is the ones that we wanted. Cool. 54, I squared C1, 5400, 5800. Cool. Those are the ones. Okay, cool. And and then, oh, apologies. This is gonna be a little bit not cool. My headphones are dying and I have to change audio.
Hello, 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 hello. Okay, cool. That sounds cool. That sounds like it still works. Even if my headphones die, so let's keep going. Um, so the first thing we needed to do is we need to define our I squared C peripherals, which we have. I see here I squared C1 and 2 APB1. And then I think the next thing we want to do is build an I squared C register definition. Remember, every time we add a peripheral, we add a register definition, so that way we can kind of control how we configure and use the peripheral. So I think the first thing we need to do, let's do here, and then let's say I2C. I2C. I squared C takes me so long to type here. To type def struct, and then let's go in here, and then we could say I squared I2C register definition type, and then let's go from there. So we need to basically use, remember we do have our document here we can use to identify our registers. I want to go down all the way to the register map. So this is one. I think we have CR1, CR2, OAR, OAR2, DR, SR1, SR2, CCR, TRISE, and I think all of them are 32-bit and 32-bit, all of them, and I don't see any blocks, only reserved blocks like that we need to skip. So let's quickly in 32T CR1, and let's just copy that and see. I think it was CR2, 2, and then OAR1, OAR2, I think, and then it was DR is just one, and then I think after DR we had SR1, and then we had SR2, and then after SR2 we had CCR, and then after CCR we had, I think, TRISE. Let's just quickly confirm CCR, TRISE. Okay, TRISE. Okay, cool. So that's our register definitions. We can confirm, yes. CR1, CR2, OAR1, OAR2, DR, SR1, SR2, CCR, TRISE. Okay. CR1, CR2, OAR1, OAR2, DR, SR1, SR2, CCR, TRISE. Okay, so we have a register definition for I squared C. And then now the next thing we need to do is probably define, we need to define actual, how would I definition. So let's define our APB2, SPI 1, 2, 3, SPI 1, 2, 3. I have a feeling SPI 1, let's see, SPI 1, SPI 2 and 3 are on SPI 2 and 3 are on APB1. So 2 and 3 APB1. APB1 port addresses. So let's quickly add SPI1 and 2. Let us quickly add I squared C1 and 2 here. I2C register definition type pointer situated at I2C 2 base 20BR. Okay, cool. So we have port addresses. So we have an actual I2C1 and I2C2. And then I think the next thing we want to do is clock enable and disable for I2 and I2. So let's go back into our code and find low mid connectivity line. No. 103, 1632, 1628. No, which one do this? I think we're medium density. And then let's look at our RCC registers, and then we need to find out in our RCC registers we need to find out APB1 ENR. Let's go look at APB1 ENR. APB1 ENR, and then we need to find the registers that enable I2C1 and 2. Clock disable them. I2C1 to bit 22 and bit 21. Okay, cool. So let's add those. Let's look at it. Two. Okay. Define. I2C 1 peripheral clock en, and then we'll go RCC dot. Okay, something's up. There's the reason my code's not building. Build. Okay, cool. So let's this is disable, enable, okay, cool. I'll just try and get auto completion to finish to work so that I know I'm 2C1 bit clock en RCC dot APB1 ENR, and then we'll set R equals to, let's set the 21st bit 21. Am I right? 21 here at I2C1 clock. Okay, I'll copy that, and then I'll have that, and then I'll say I2C2 and then I'll say CP1, and then this is 22. Okay, let's add clock disable macros for I2C. So this is kind of like just reset. I mean, no, this is just the same thing, which is the same, and it's going to be a negation and a negation and a negation, and then we want, this is the clock DI, DI. Yeah, cool. So disable macros, and then we want register reset macros. So this is for when we just want to leave a clean, gracefully shut down peripherals. Register reset set. So I'll just actually copy this one and I'll put it here, and then I'll say I2C1 register reset, and then let's go to APB1 reset register, APB1 reset register, and then we need to find I squared C 21 and 22 again. Okay, 21. And then this is I squared C 2, 22, 22. So this code allows us to reset the registers for I squared C. Basically, after using the peripheral, and we now want to finish reset. I mean, go back. Finish using the peripheral gracefully. Basically, in order to save power when you are working on low power applications, you will have to so that you don't have like some lagging memory that is causing the processor to do stuff that you don't want it to do. Let's add some IRQ numbers for I squared C1 and 2. So I2C, 2C1, I2C2 2C2. Don't worry, I'm gonna look at the console for questions just after this, but like right now, let me do this and click. Let's break the interrupt controller. Yeah, I need this table. Yeah. Connectivity line. Sorry for covering my mouth. Connectivity line XL. No, I'm not XL. I'm gonna be connectivity line. So let's look at connectivity line. Vector table. So I'm a little confused. I'm just asking one. Let's see. Can we do if, and then we'll copy that. So it seems as though I squared C has an event, so connectivity line development. So I'm learning, so we are going wrong. So I squared C has an event interrupt and it has an error interrupt separately. So what we need to do is collect both of them so that we can use them. Okay, so event I squared C1 event is number I squared C1 31, and error is 32. Event for I squared C2 event is 33. Excuse me. Error is for 34. So we've added IRQ numbers for I squared C events and errors. So I squared C has an error interrupt and an event interrupt, and you can capture separately and use separate numbers. So let's look at the test chart. No questions so far. So that's cool. So we've added the interrupt request numbers. Let's go down. Okay, cool. So we've done the interrupt request numbers. We need to do bit positions. So bit positions, how do I close that? Let's go to SPI. I just saw an issue. SPI registers, and then I think it's the SR register, and then we have the FRE. There's no FRE register, so there's a busy at the end, but there's no FRE. So let's remove that. That's not for you. Cool, thank you. So I2C bit definitions. So in our implementation, we're not going to use all the registers, since we're going to implement just like a very rudimentarily I2C. I mean, in the beginning now, we're gonna do it from scratch. The whole point of this series is that we do something from the scratch side. I'm more interested in implementing the rudimentary drive from nothing than actually implementing the very like involved driver at the end. So because there's a lot of content, there's a lot of material and content covering how to kind of do DMA stuff and how to kind of do advanced interrupt stuff and all of that stuff. But I find that there's no content or material showing you how to start from nothing, and I'm more interested in us starting from nothing. So our rudimentary implementation of I2C is not going to use all the registers. At the moment, we're only going to use let's go back to the book, and now let's go back. So I2C registers, we're gonna use control register 1 for setting up, because this one we need the acknowledge, we need stop generation, start generation, we need stretching control, we need that. Okay, control register 2, let's see, errors, events and errors, we need to catch them. We need to use a frequency block so that we can set the peripheral clock, and then we do need to set the addressing. So we need OAR1, not OAR1, this is just right into circle, we don't need that. Okay, let's look at OAR2 data register. We don't really need that, that's just a 16-bit thing we can just use. SR1, SM bus, timeout, P Sierra, overrun error, acknowledge failure, bus error. We need this to tell us if anything error. The RTX register empty, RX register not empty. Yeah. We need this one. So we need SR1, and then we'll need let's see, SR2. SMB default general call. Yeah, we need that. Busy, yeah, we need that. Master slave mode, we need that. That's cool. We need SR2 as well. CCR, clock control. Yes, we need this for this part. We need to set up the clock control so that we generate the correct frequency. I just dived into this, and while I understand how to do it, I need to kind of explain it a few times before I can completely grok it and understand it like backwards. So bear with me if my explanation is unclear or something. Let me know and I'll kind of get back to you on how to do that. So first of all, let's add the bit definitions for the ones we're gonna use in SR1. Okay, cool. So let's do CR1. We need the CR1, let's go from the beginning. We need peripheral enable. We probably need no stretch. We need start generation, we need stop generation, we need acknowledgement enable. We need those. So, and maybe stop software reset so that we can like clear the thing. Okay, so let's put those in. This one, hash define I2C CR1 PE. Okay, so this is peripheral enable with 0. And then I'm gonna copy this so that we can kind of have an easier time. We said we need, what's the next one we need? So peripheral enable, yeah, and then we'll need no stretch, number 7. No stretch. 7. I think number 8 will also need start and stop. Start. 8. Stop. 9. And then acknowledge control should be 10. Okay, cool. I mean, if you can always just put everything in, but it will take you a long time. There's no buts. It will take you a long time. And then let's see, which is the last one. We need 15 as a software reset. So SWRST number 15. Okay, cool. So let's go to CR1 used CR1 bits. Okay, cool. So let's now do CR2 bits. Okay, cool. So I'm just gonna copy this and start from there. Okay, so let's go back to CR2 and see which ones we need. CR2, what do we need? We need frequency, yeah. We will need interrupt enable, error interrupt enable, event interrupt enable. Yeah, I think that should be in. And buffer interrupt enable. Yeah, cool. So that's cool. So let's start with frequency. Okay, and then we're gonna go. This is also CR2. Yeah. Okay, cool. So let's go to, I think, interrupt error enable, and that's bit 8. CR2 interrupt event enable, ITEVEN, that is bit 9. I think buffer event, IT buffer enable, ITBUFEN, and that's going to be, I think, 10. Perfect. Cool. Okay, so we need, I would say, SR1. So which ones? I think we're going to probably use all of SR1. Let's go look at it. SR1. Okay, cool. Oh, bit OSB, bit 1 address, bit BTF, add 1 0, 10-bit address, stop detection, RXNE, TXE, bus error, arbitration lost, acknowledge failure, overrun error, PC error. PC error from timer. Okay, cool. So we're not using bit 13, we're not using bit 12. So I'll just, I think this is almost the same as a F4. So I can copy from that. Okay, cool. And then let's look at SR2. SR2, probably we want MSL, we want busy, we want TRA, we want gen call, we do want dual F. So, okay, cool. These ones are the same as okay, cool. SR2 and I2C bits. Okay, and I want to go here and say and SPI bits. Okay, what else? And then after we do this, we get to the end of the file and then we realize what else we need to do. So let's go into our drivers and then include, let's make a new file, new header file, STM32F1xx I2C. Let's make that, and then in SRC, let's make new source file STM32F103xx I2C.c. Okay, so let's make those two files. Let's go into spi.h. I2C.h. I just want this name. And then we're going to our device header and we want to, I would include it. Okay, cool. So we basically have the MCU, I'm going to check for questions. We basically have the MCU specific stuff done, which is defining our bit positions, defining our ports, defining our clock enable and disable markers and all of those. So I'll actually venture a comment here. Just a moment as I check questions. Target. Target. STM. 4. Open the small window, pull it here. Git status. Git add. Oh, it's in here. CD STM. Okay. Status git add drivers git commit -m add bit port and bit definitions to MCU header and I2C files. Okay, cool. Push. If you want that code, you can have it already. Okay, cool. So let's now go. Oh, branch dash m I2C work. Git branch I2C work. Git push okay, cool. So I2C work. Rename the branch. I was using the old branch for SPI. Okay, so far let's quickly just do a very brief recap. So added we've added the we have added the bit definitions for I2C in the application, and then we have also we've added the bit definitions for I2C in our MCU header, and we've also defined peripherals and such. So now I think the first thing we need to do is kind of like venture out and see what we need to do so as to enable so as to how do I phrase it? Sorry, OBS sometimes makes it hard to like access your chat without looking at your stream, and that made me lose my focus on what I was doing. Okay, cool. So the next thing, the next step we want to do is kind of let's go into our I2C header file, and let's kind of add all the conveniences we need and all I would say the functions that we need in order for us to ensure that we have in order for us to ensure that let's see. In order for us to ensure that things are okay. So yeah, this should be thin. We should be able to. We should have this here. So I don't know why we don't have this here. But it's fine. That's why I went into that file originally to copy that. Okay, cool. So I2C. So let's start by adding. Remember, with every peripheral, this is kind of becoming like standard because we have the SPI one, we have the GPIO one, we're now at I2C. So it's I'm almost like going to forego explaining what this is unless someone asks the question. So let's add a config struct that we use to configure, and then let's add a handle struct that we use to now actually use the definitions of type def struct, and then configurable items. So I think configurable items for I2C I2C protocol. So let's go look at the I2C kind of definition. Let's see, we can quickly find out the configurable items. So protocol. No, I'd like something simpler. So we probably need to configure the speed. Okay, and then see, you need an address. You need an address if you're a slave, so you need to say who you are. If the device that is using the driver is going to be a slave, it needs an address, so we need to be able to configure the address. And then we need to, if we look at our document, if we look at our reference manual, you will see that acknowledge is not enabled by default, so we need to provide a way to enable acknowledge. And then I2C has something called a duty cycle. What is a duty cycle? Duty cycle in the first place. What is a duty cycle? Nice. What is a duty cycle? So a duty cycle is simply the ratio of time a circuit is on compared to the time a circuit is off. So if you have a wave, the duty cycle is the ratio between the time it's high and the time it's low. So if this is 5 to 5, this is 5 seconds and this is 5 seconds, then the duty cycle is like 1 1, if that makes any sense. So in I2C, at some point we will need to choose the waveform, and in order to do this we will need to provide a duty cycle which will define kind of the frequency that we were going to use. It will come as we go along, but so those are the 4 configurable items. Just to recap, the speed, the clock speed, so the device address if it's a slave, the acknowledge control so that we enable or disable auto acknowledge, and then the duty cycle so that we can kind of decide the waveform of I2C. It might seem a little confusing right now, but the farther we go into it, it'll get to a point where you're doing it and you're realizing like this is why we need this. So let's go into 32T I2C FCL speed. Okay, cool. We need to configure that. You int 8T I2C device. So I2C works with let's go back to here, or maybe here. I2C works with, as you can see, 7 or 10 bits. We're going to cover the 7-bit one. 10 bits will come later. I don't know if we'll cover it on stream. If someone requests it, we can cover it, but rudimentarily we're going to start with the 7-bit addressing. So that's why the space is 8 bits. Okay, cool. So int 8T. So this is just I2C control because we only need 1 or 0. I2C ACK control. Okay, and then you int 16T I2C FM fast mode duty cycle. Okay, quickly before we go on, so the waveform for I2C SM duty cycle, I have not even so I2C has 2 modes: standard mode, which is anything under 100 kilohertz, that's standard mode, and then fast mode, which is anything above 100 kilohertz. But then when you get to fast mode, the waveform, you can have 2 different waveforms, and I'll show you this one here. It says here You see, when you're in fast mode, duty cycle. When you're in fast mode, if you're in fast mode, you could have T low is equal to T high, which is equal to 2. And then if you're in fast mode, you can have T low, T high, could be a ratio between 16 and 9, 16 to 9 ratio. And this, it's kind of, when we get to calculating this, you'll see why we can use this. For ST, these two are required in order to, this is our fast mode and standard mode work in ST. And we're going to use these two factors to kind of modify our waveform so that we get the correct frequency or the correct hertz of the clock so that we can use it when speaking to our device. So let's quickly add that. Okay, so config type and struct. Okay, go. So, and then handle struct. So let's start with that. Oh, there is an issue here. I2C config T. Okay, cool. Type def struct. Okay, so we're making a struct that is also a type. Okay, cool. And then in here, I think I want to I2C to red def, and then this is peripheral I2C, yeah, X. Some I2C peripheral, I2C config T, and then this is which peripheral? Okay, I'll I2C config. So basically the way we can understand this, which peripheral excuse me, how to use this peripheral. So we have a handle structure, we have a config structure. Okay, cool. So let's define a couple of type options that are only available so that when we have like some defined how would I say, some defined speeds, some defined how do I say it, some defined, like these things will not change. We don't want the user to provide it so that we are good. Speeds. Define I2C SCL speed. Standard mode. 100 kilohertz. Define I2C SCL speed. Fast mode. What is that? 4 kilohertz. Okay, so arc control could be on, could be off. Okay, so this is define I2C arc EN 1. Define I2C arc EN 0. Okay. Fast mode duty cycles, because the one standard mode is only, it looks like it will be 50%, which is equal. So we only have duty cycles to define for duty cycle options for fast mode. I2C I2C FFM duty to 0. So you see here we have like FM duty 2 is this 2 and it's 6 9. Okay, 0. Okay, cool. So we have the initial header. Okay. Quick build. Ooh, saw something. Thank you. Quick build to make sure all our code that we added is good. Okay, cool. Good. So this add drivers. Good. Commit. Build initial I2C header. Okay, cool. So next thing. What are we doing next? So let's add some headers to our file to define the APIs that we are going to support. No? Yeah. Okay, cool. APIs. Okay, so init and the init. And this is like the basic ones. Yeah, so right now I'm kind of like moving as though I'm writing the SPI header, so, or the SPI file. So I2C init so, and this will take I would say a handle, right, to C handle 2 P I to C handle. Okay, and then we can have the same one. And then this is the init, and this one can actually, instead of taking a handle, it can just go to the register definition actually. X. Okay. And then we also need the perennial one, clock enable one. So let's define one, void I2C b clock ctrl. Okay, I2C reg def I2C to C X and then en or en u int 8 t en or dr. Okay, and then later we'll add data tx and rx. I2C is going to be different because so master tx and rx because master needs to set up stuff. Like master needs to do stop and start generation, and then needs to arc and stuff. Master must they'll be different. Like it's different when you're sending as a master, and different when you're sending receiving as a master. So slave tx and rx. We won't cover that today. We'll cover that later, and then IRQ config and priority. Handling will come later. The reason I've implemented this for a different board before, so I'll just put in here. Handling will come later because handling is different. Like you saw, I2C has error events, error interrupts, and event interrupts differently. So the way we are handling them is going to be completely different. So we'll add that later. And then just like SPI, we have the peripheral control, if you remember. Here in CR1, we have this bit 0, peripheral enable and disable. This, you need to do all your configurations while this is 0, and then enable the peripheral. Just like we did with SPI. You configure the peripheral and then you enable it, because some of this configurations only apply if PE is 0. So it's good to just enable the peripheral after you've done all the configurations. And then I'll add those here. And obviously we'll need there's some flags we're going to use. And then, like we discovered in SPI last time, we probably are going to need an application event callback, and just so the application can, like, whenever we are using interrupts, we need a way of letting the application send data, telling the application an interrupt occurred or an event occurred and such like that. And this is going to be for that purpose. Okay, cool. So what else did I want to do today? It's 10. It's already been an hour since we started. So let's see. We can work on basic initialization. So I would let's first go to the I2C. First of all, let me check for questions. No questions. Let me check here for questions as well. No questions. No questions on WhatsApp. No questions on Discord. No questions on YouTube. Cool. Let's call Discord. Discord might not be open. Let's open the reference manual and look at the functional description of I2C. I'm gonna quickly read this, and then we can come up with what I'm looking for is pointers on how to initialize I2C, and more likely at the moment just pointers on how to initialize I2C as a master, and then I can do that initialization, and then from there on we can maybe see if we're going to do the slave one, and then we'll get there. Seems like Erica. Okay, cool. So let's keep on. Let's keep on. Let's keep on. Let's read this in verbose. As always, this is what I always say to do. I'm applying my own advice to myself. If you read the data sheet or the reference manual or the generic user guide in detail, it's going to tell you all the stuff you need, and then from there on, it's easily enough to like. Most of embedded development is just writing to bits, and if you can do that, or writing to bytes, and if you can do that, you should be able to. And the reference manual or the datasheet will tell you what to do. So let's read this and see if we can figure out our way of initializing I2C, and then we can maybe stop at that or implement it, depending on how I feel. In addition to receiving and transmitting data, this interface converts it from serial to parallel format and vice versa. The interrupts are enabled or disabled by software. So this means whenever it says by software, it means you're responsible for it because you're writing software for it. So the interrupts are enabled or disabled by software. The interface is connected to I2C bus by a data pin, SDA, and a clock pin, SCL, and it can be connected with a standard up to 100 kilohertz or fast up to 400 kilohertz bus. Okay, cool. So we know that. The interface can operate in one of the following modes: slave transmitter, slave receiver, master transmitter, master receiver. I think I mentioned this before. So we'll have master transmit and such, and slave transmit. So, but we're not worried about TX and RX right now. I just want to know how to initialize a peripheral and hold it. By default, it operates in slave mode. This interface automatically switches from slave to master after it generates a start condition, and from master to slave if an arbitration, loss, or a stop generation occurs, allowing multi-master capability. Okay. In master mode, the I2C interface initiates a data transfer and generates a clock signal. Serial data transfer always begins with a start condition and ends with a stop condition. Both start and stop conditions are generated in master mode by software. So, by software. Remember, whenever you see by software, means you're responsible for doing that. So, you're responsible for generating start and stop conditions. In slave mode, the interface is capable of recognizing its own address, 7 or 10 bit, and the general call address. The general call address detection may be enabled or disabled by software. So, general call address means there's an address that if used, this thing will, it's like a memoized thing, so it will always accept that address. Or, alternatively, if you have set an address, as in your OAR or OAR1 or 2 registers, the device is capable, using hardware, of recognizing its address. Data and addresses are transferred as 8-bit bytes, MSB fast. The first byte following the start condition contains the address, 1 in 7-bit mode, 2 in 2-bit mode. The address is always transmitted in master mode. The ninth clock pulse follows a 8 clock of cycles of data transfer, during which the receiver must send an acknowledge bit to the transmitter. Okay, cool. So by default, let's look at this. By default, the I2C operates in slave mode. To switch from slave mode to master mode, a start condition generation is needed. The peripheral input clock must be programmed in order to generate correct timings. Okay, cool. So we need to do the peripheral clock, and what else? Okay, cool. So let us do this. So let's start by let's go to our header file. Live coding. This is how it goes. We're all researching and learning at the same time. This is how it goes. There's quite a few things here that we can throw out in quick succession. IRQ config and I2C config are the same as the SPI ones that we had made earlier, so we can definitely quickly just copy those in. Let's just copy those in because they're going to be the same as the things that we've made before. rq config and rq. So let's go here. Let's go at C. Let's see. Let's add this. So this, and then let's maybe, I think in order to do that properly, we need to add the header file. Okay. Let's add this. Okay. So this will enable us to do IRQ configuration and the configuration, and then remember we have the peripheral control bit, the one that enables or disables. So let's copy that in. It's going to be the same as the SPI one. So let's look at the SPI one, peak clock control. I think it's gonna be peak clock control. No, peripheral control. This one, CR1, PSP. Okay, cool. So let's copy that, and then we can put it into I2C. So cool. That's peripheral control. Header. We've done that. We'll do that later when we know which flags we want. We've done that. We've done that. Peak clock control. Peak clock control. We can also. This is basically just using the functions that we have already defined. We'd already defined these, so let's add that. And I think this only has I2C too. Okay, so this is the init, that's fine. And then we also need that's the init, that's fine. Okay, so the init is in. Let's quickly build init. Okay, and then we're done with the string for today. Ooh. So let's explore this. So what are the, let's now, the usual, int 32 t temp reg equals 0. Okay, cool. So let's go. Let's first of all set up arc control. So how do we set up arc control? How do we set up arc control? CR1. Sorry for covering my mouth again. Arc control. This bit is set and cleared by software and cleared by hardware when PE is 0. This bit is set and cleared by software. Okay? And cleared by hardware. So when PE is set as 0, when we disable the peripheral, this will be cleared. By default, this is cleared, so no acknowledge is, so basically acknowledge is not on. So let's actually set that. So temp reg equals p handle dot hcconfig dot app control. It's in which one? It's in the 10th bit of CR1, so I don't think I should be I2C CR1 app control. Yeah, 10th bit. And by what is this? 10. Okay, cool. And then I think that's what we need to do for CR1 for now. So let's do handle dot, let's take the peripheral itself, dot CR1 and then equals temp reg. Okay, that's what we need to do for CR1. Let's look at CR1 again. CR1, stop, start, no stretch. We're not using these ones right now. Okay, cool. Okay, CR2 config items. Okay, these ones may be a little bit more complicated. Temp reg equals 0. Okay, cool. So CR2, we need to do CR2. So CR2, I now want to look at CR2. So which ones do we need to enable in CR2? The interrupt ones, we'll get to there. Frequency to set the clock. Okay. And then we also need to do CR2. What else was CR2? Clock. That's it. Okay, cool. So let's read the frequency thing. The frequency bit must be configured with the APB clock frequency value. Okay. I2C connected to APB1. The frequency field is used by the peripheral to generate data setup and hold times compliant with the I2C specifications. The minimum allowed frequency is 2 megahertz, and the maximum allowed frequency is limited by the maximum APB frequency and cannot exceed 50 megahertz. Okay, cool. So I2C is running on APB1. I think we need a data sheet. I think we need a data sheet for this to be able to understand this. We might have to stop here. Data sheet. So bus information. Oh no, where do I find bus information? APB1. Okay, cool. So APB1 is running, it depends on which clock we're running. So if we're running, there's 3 clocks. There's HSE, HSI, and PLL. Let's just look at the clocks. So clocks. So 3 different clock sources can be used to drive the system clock. HSC, oscillator clock, HSI, HSE, and PLL. So PLL is like a software defined one, and then HSE is an external clock. So that would be this little guy. This guy. I don't know if I'm showing anything. This little oscillator here. And then HSI is an internal software defined clock, as far as I understand it. So let's look at it. So clock, it's a 8 megahertz HSI into software, and then it goes into AHB1 prescaler, and then it's get into APB1 pre, so it goes to, it comes in at whatever level it is. This is 8 megahertz, and then it goes into software, and then it goes into the system clock, which gets into AHB prescaler, and then it goes into the APB1 prescaler, and then from the APB1 prescaler to APB1 peripherals. So in order to calculate this, we need to find out, number one, which clock has been selected, okay? And then after we find out which clock has been selected, is it a HSI or PLL or HSE or LSE or LSI, okay? So those are the clocks available. Find out which clock has been selected, which clock is being used by this application. And then the next thing we need to do, what is the value of the AHB prescaler? and then we need to find out what is the value of the APB1 prescaler, and then kind of like clock 8 megahertz, divide by whatever prescaler is the HP, divide by whatever APB prescaler. That's the frequency that we have. This is the frequency that we hand into frequency, and this is the frequency that we write into. This is the frequency that we write into the CR2 frequency field. So we need to find out what frequency it is. Let's write a function. Let's write a function that does this clock stuff for us. Okay. So uint 32t RCC get p clock PCLK value takes a void, returns a 32-bit integer. Okay, uint 32t uint 32t p clock 1 return Okay, cool. So let's now find the source clock. Okay, find source clock. So we need, in order to find the source clock, I've done some digging, and I know this is in the RCC registers, and we have in the RCC configure registers, actually CFGR, and then I know, I think it's register 2. System clock switch status. So 00 HSI uses a system clock. 01 HC uses oscillator clock. 2 PLL. Okay, so we know which clock that we're using based on this, if that makes any sense. Does that make any sense? Yes. Whew. I'm trying to think. So HSI, HSE, PLL. Okay. Okay, cool. Let's add a calculation for that. So we'll need in here we'll need a temp. We'll need a system clock. And then let's go here, and then uint 8t CLK SRC HB prescaler APB prescaler. We're gonna use those values as we go along. Clock SRC equals to, if we read from that register that we just saw, RCC dot CFGR, and then we go to 2, we push it out by 2, and then we're going to clear all the other bits, OX3. This should give us a 2-bit field that tells us which clock source we're using. So which clock. Okay, if CLK SRC is equals to 0, which is system clock is equals to what? Okay, cool. So I was looking at a few documents, clocks, isn't it? Okay. 8 megahertz, 8 million. HSI 8MHZ, and then HSE 16 MHz. Okay, we're not gonna handle PLL for now. So let's look, and then we still need to go to this one. Okay, so if 0, we are on HSI. If we are on 0, we are on HSI. 1, 2, 3. 1, 2, 3. Okay, cool. Else if CLK SRC, we are system clock 1, 6, 1, 2, 3, 1, 2, 3. No, it's 1, 2, 1, 6, 1, 6, 16 million. 16 megahertz. Yeah, that's fine. Else, if CLK source equals to 2, calculate PLL source. This is a bit more advanced. We won't do that now, but later along the line, if we want to explore, we'll find out. So let's find out with AHB prescaler value, yeah, which is temp RCC CFGR, and then we want to do that. How many? Which one contains the HB prescaler value? HB prescaler value bit 4 to 7. Okay, so 4. I want to clear all 111s or XF. So we'll mask it against 7 to get the 3 bits that we want. If temp 8. Okay, cool. So here's the value. 0 not allowed. 8 is divided by 2. 1, so there's 2, 4, 8, 16, 64, 128, 256. So let's make a array with AHB prescalers, basically. Okay, so HB prescalers. So if 8, then HB equal 1. Else HB pin equals HB prescaler. Now let's take the position temp minus 8. So the value minus 8. Okay, and then this should give us either divided by 2, divided by 4. You see, does that make sense? Like we will pick the divisor from the array based on what we get from the prescaler value reader. Cool. Then APB1 prescaler. So temp is equals to 0, and this should, if temp 8. Okay, let's look at the APB1 prescaler. I think it's gonna be the same. So okay, cool. This is 4. Okay. This is 4. So it's from 4 all the way to yeah, this is 4. Okay, so let's use 4. might be wrong here. My code might be. I'm getting quite a PB. Prescaler. One. My code might be not as right as I wanted because I'm getting a little tired, but we're getting to the end of the stream, so I want to push together and finish APB1 prescaler. Let's add those values that we saw there to 416. Let's add these values here. We just saw this 24816. I'm getting these ones 24816. Okay, and then we'll be like, this is gonna be APB1 prescaler, and then we're going to have 10 minus 4. I think that should be the one. And I think there's a calculation I'm missing there. There's this read. This read. Okay, this is the read I'm missing. So this is configure, move, go into RCC CFGR, right shift by 10, which means push everything from here out. And then we want to mask it with 7 so that we just get the the units that we want. And there we go. So return P clock 1. And then let's now do so P clock 1 is equals system clock divided by HBP, and then all of this divided by APBP. And then return P clock. Cool. So now that we have the system clock, now we can go back to, we know the frequency at which the system clock, we know the frequency at which the system clock is running, if that makes any sense. And now we can use that to kind of program our CCR register, which needs us to give it the frequency that we want. So CR2 temp reg, okay, so we have the sequences RCC get PLK value over 100 1 million. So we get this is in how many kilohertz we want from megahertz, I guess. PI2C handle dot I think this one dot CR2, and then temp reg equals temp reg. Let's 3F. So we just want to mask everything else other than the things that we want to set, so that we just set the one we want. Addressing if in slave mode. Okay, go. To do handle 10-bit addressing. So we would handle that here, and I'm going to probably just do temp reg. So we're gonna get the address that we got from the user and set it as in our OAR address. Temp reg equals, so let's set this equals p handle dot description config sqc device address, and then we're gonna set it as one. Why do we want to do this? This is because in OAR1, we can go look at this. OAR1, we should see bit 0 interface addressing. 7-bit address, we don't use this one. 10-bit address, we use this one. So if we don't use this bit, the application knows that we are in 7-bit. So that's why we are left shifting this by 1. And then temp, and then remember we also have in OAR1, I think bit 14 should always be kept 1 at software. I'm only knowing this is here because I've read all of this before I did the stream, obviously, and that's why I'm kind of like, so temp reg, and then we want to do 114. Okay, so 14 should always be kept as 1, and then PIS handle ref manual demands this. Okay, PIS handle dot get cx dot OAR1 equals temp reg. And then let's do CCR register. So I know how to do this. Is the one I know how to do, but my explanation of it is not where I want it to be. So might not be what I want. Unit 16T CCR value is equals 0. So let's go look at the CCR register, try and understand it, and then come back here. CCR register. FP clock 1 must be at least 2 megahertz to achieve standard mode I2C frequency. It must be at least 4 megahertz to achieve fast mode I2C preference frequencies. It must be a multiple of 10 megahertz to reach the 400 kilohertz maximum. Mega is more than kilo. I think so. The CCR register must be configured only when I2C is disabled. So PE is 0. Okay, so like I said, there's a lot of things that you have to do. You have to configure the whole thing and then enable the peripheral. So this is clearly one of those. Okay, so number 1, we need to do fast mode, select whether we're in fast mode or standard mode. And then once we're in fast mode or standard mode, we can select duty, which duty we want. And then once we select the duty cycle, we need to calculate and set the CCR. So for instance, in standard mode, to generate a 100 kilohertz S clock frequency, if the frequency is 8, which is 8 megahertz, I think, T to P clock 1 is 120 nanoseconds. So if it's 8 megahertz, 8 megahertz is how many hertz is per second. So megahertz is going to be 8,000 times a second or something. So how many times, how long does the duty cycle go? Okay, so for standard mode it's going to be 8, frequency is going to be 8, and then 125 is going to be the TP clock 1 is the cycle, up down with 125 seconds. So CCR must be programmed with 28, which is equal to 40 decimal times 125, which is equal to 5,000 nanoseconds. So I'm going to implement this. Basically, this is the formula I'm going to implement here. And I2C communication speed is equal to F source clock 1 over T high plus 1 over T low. The real frequency may differ due to the analog noise. Okay, good. I'm going to implement this, and this is also, I think this deserves as like its own deep dive video where I kind of break it down, because some things are in times and some things are in frequencies. So it's some things are in seconds and some things are in hertz. And basically what we need to do is convert. It's like the other day I was at Songo, I was helping a kid do simultaneous solving of two equations. So you have like 2xy plus 1 is equal to 5, and then 3xy is like a more complicated equation on the other side. And you basically, if you simplify the both of them, you can find out the value of x in terms of y and the value of y in terms of x, and from there on you can almost take all the common factors and put them together, and that ends up fixing your equation. So this is kind of the thing we'll need to do here, and I think this deserves a deep dive video in itself. If pi squared handle dot I2C config dot SCL speed, if this is less than or equal to I squared SI less than or equal to I2C SCL speed standard mode. So if this is less than 100 kilohertz, then CCR value, this one is really simple. So CCR value is equal to RCC get peak clock value over 2 square handle so you can feed dot speed. Where did I get this from? Right here. See? Okay. So SM mode, T high that, T low is this. So if I get the value of this plus the value of this is T total. Okay? So this is also the other thing. T high, T low, value of this plus the value of that is T total. And T total here is what we need to set into the CCR. Value of this plus the value of that is T total into that. Okay, cool. So that's the that's what we need to do. Yeah. And also, so let's look at it. It's always in duty is 0 and SM mode is 0. So we don't need to touch duty or mode fields if we're doing standard mode, if that makes any sense. So they're already set for us. So we can finish here. Temp reg so basically we are cool. So that's if we're in standard mode, this is what we need. Okay, so else fast mode. Okay, fast mode has two options. You see, fast mode has this option and also this option, depends on the duty. So let's set, first of all, we need to set fast mode in the mode bit and then the duty, and then we go for it. Okay, cool. So let's go here, fast mode. So temp reg, okay, cool, temp reg is not or equal to we're in fast mode. Yeah, this bit definition 15, fast mode 1. Okay, cool. Okay, we didn't add the CCR registers because this is how we're going to use them. And then let's do duty. So temp reg pi handle dot I2 squares fig I2 duty cycle. So this duty cycle is going to be, you remember, if you go to our here, you'll realize that we made two macros for duty cycle, 2 and 16.9, 0, 1. And depending on which one you gave us, we're setting them here, 0, 1. Okay, so That's fine. That's where it comes from. Okay. We'll set the duty cycle, and then now let's do CCR. If P handle dot I2C config dot FM duty is equal to I2C FM duty FM duty 2. Okay, so if the FM duty is 2, we want to be CCR value equals did I? Oh, okay, cool. RCC get P clock value over 3 times PI squared handle dot config dot I2C speed. This is given us here. So this is 3. 1 plus this one. The speed. This is defined in times here, time peak clock 1, but we can convert this into a frequency so that we actually end up getting CCR. Okay, makes any sense? And then here, and then here, else, let's do that. 25. Where is 25 coming from? So CCR, 2 CCR plus 1 CCR times that. Okay, so that's 3 CCR times that. Okay, and what is this? This is our clock value, which is here, speed. Okay, and then we divide by this to get a frequency. Same here. So it's 9 times CCR, 16 times CCR times the clock. So what is this here? Okay, 9 plus 16, 25 times those. Okay, cool. So we can get that 25. Make sense? Should make sense, at least. And then we can do temp reg equal CCR value. Let's zero out everything else. 0 cross FFA. Okay, cool. And this brings us neatly to here, where we do PI2 handle dot PI squared X dot CCR equals temp reg. Finally, so basic initialization of I2C done. Okay. We'll check for any questions. No questions so far. Understand. Build project. Okay. These are not comparisons. These are. I apologize. I put comparisons here. Not comparisons, built. I have a feeling this is something like temp equals. Yeah. Build. Okay, so let's go to the last error where we're seeing an error. 126 CCR value. Is it that you do not have a termination? Okay, and that's it for today. Okay, let's look at what we did. So we added some header. In the headers, we defined some applications, and then we went into our. Okay, cool. So this is not GPIO.h. No. GPIO.c. This is utterly wrong. This should be. I should only be including this guy. So I am wrong. Okay, cool. That's fine. Build this. Okay, perfect. Looks like. Cool. So check for more questions. Any questions? Yeah, sure. Okay. Git status. Git commit. Cursory correction of imports plus initial I2C init. Perfect. Good. Push. Okay. Okay. Perfect. Okay, awesome. All of this code is up. Please feel free to check it out. Feel free to leave me ideas on what to implement on my channel. Leave me comments and join the Discord that's in our link below. And let's work together. It's quite fascinating, actually getting faster at reading these data sheets and actually being able to use them to implement the drivers that we want. Really is feeling good, so I'm quite happy to keep on with this, and we'll see. At some point, maybe after UART, we'll start like kind of using KIMSys. And that way we don't have to re-implement all the stuff, and we can go into more fun stuff such as implementing applications rather than building drivers. But it's good to get used to how drivers are built so that you know when to go and look for something, how to go look for something, and it's also good practice to build drivers that are kind of easy and someone else has already implemented. That way you can always go cross-check your work with existing work, and then that way when you're developing a driver for something that doesn't exist, then you kind of have this assurance that you're walking along the correct path. Anyways, that was the Wednesday stream from me. Thank you so much for watching and for pushing out, and see you next Wednesday. See you Friday to finish. Ooh, it's a big promise. See you on Friday to finish TX and RX APIs for I2C. Earlier than this, 6 in the morning. Cheers.